Okay, so we're on the road now. Saturday. So we're gonna go to the Dominion Radio Astrophysical Observatory. So there's three kinds of observing you can do of space itself, right? As you know, humans with current technology we have. So we got optical sight. You're optically sighting objects in space and observing them, and then you've got radio observatory, which what these guys are doing is they're reading radio waves from the electromagnetic spectrum, various frequencies, and they use that to interpret various different things through that. We're gonna go see CHIME, the Canadian Hydrogen Intensity Mapping Experiment, the synthesis telescope as well, and that's all radio waves. Studying radio waves there. There's no optics there. The final one that you could do, if you were a professional, is the stuff that NASA does. So the Hubble Space Telescope and everything. Because of the atmosphere, we can't study gamma radiation, UV radiation, and infrared in the same way. So infrared especially because you got all the light pollution down here. So what they do is they launch satellites into space to take pictures and measure these phenomenon outside of the atmosphere, because they can get much higher pictures and resolution by actually physically having the telescope in space. But obviously if you wanted to view through that, you gotta work for NASA, right, or some kind of space agency. The Okanagan, due to the fact that it's kind of a dry desert area, and it also is up in elevation, happens to be a hub for astronomy. It's actually one of the main contributors in the world for astronomy. There's a few facilities out here that they do astronomical studying and stuff. So tonight, a special surprise, we're gonna go see Jack Newton, who is a amateur astrophotographer, regarded as one of the best in the world. Discovered over 200 objects, and Jack runs an observatory. We've been fortunate enough, because he's very kind, to let us come and observe through his telescope and kind of learn a little bit about what actually is going on in space. CHIME, Canadian Hydrogen Intensity Mapping Experiment, which is what is at this facility, which we're going to go see. It studies redshift. So what redshift is you have you have an electromagnetic spectrum and you've got colors, right? And redshifting, the concept of it, redshift, blue shift, but the concept of it in cosmology is basically when light is coming towards you or being shortened, it goes to the blue end of the spectrum, right? Because the waves are getting shorter. And then when light is traveling away from you or expanding, like the universe is, the wavelengths progressively get more and more red. So when you're looking in through a telescope, the more red an object appears, the further away it is in the cosmos. And so cosmologists and astrophysicists and astronomers, they use this to figure out distances. And back in the day, Galileo and all those guys, that's what they did. So there's this particular kind of star they use because it has a pulsation. So it's called the Cepheid variable star, and it basically pulses light. And they know, they learn the timing of the pulsations, and then basically they observe the spectrum, the color spectrum of the light. And then they have a whole set of calculations they do based on, the wavelengths. And so when you go to this facility, they'll say oh, this telescope it studies 20 meter wavelengths and wavelengths of 6 centimeters. And so when they say that, they literally mean if you could see the waves in real life, I would take a tape measure and I'd measure from crest to crest, and you would be 6 centimeters or 20 meters, right? So they have a calculation and the frequency of the wave and all that, and that's how they calculate distance, right? So that's how they know light years and stuff. And light, the speed of light is obviously the fastest traveling thing in the universe. So basically they use that as the speed because it makes sense, because everything in the universe is light in some form or another. And they have these variables, right, of expansion of the universe. Basically you could interpret it as how far away are they studying the universe, right? So the light that's traveling, theoretically, we could see all the way back 13.5 billion years. That light is just reaching us now, but the universe has also been expanding since its beginning, right? So the actual size of the universe currently is 26 billion years, and it will progressively get bigger and bigger as time goes on, but none of us will be here to see that because we're talking literally billions of years here.
So when they say we're studying 0.8 to 2.5, what they're basically saying is there's certain time periods of the cosmos that they're trying to study, and they're studying the hydrogen in the cosmos because hydrogen is the most abundant element in existence. Like it's water, H2O, basically. So they study hydrogen and the spectra of hydrogen to basically understand the cosmos. And what CHIME is doing is mapping the expansion of the cosmos. So these people at this observatory are basically learning and observing how the cosmos is actually expanding at the rate at which it's expanding, because it's speeding up. They initially thought, due to the Big Bang and momentum and everything, like that it would, the initial inertia from everything moving would eventually slow, but it didn't. It's actually getting faster and faster and faster. They're trying to figure out why that is. Nobody knows, right? There's theories. Everybody's got an idea. There's a lot of things that kind of relate to optics that we were talking about before. So, saying before with the builder's level, the transit and the theodolite, those have optical, they're called refractive telescopes. Light does two things, right? It reflects and refracts. So you can think of refraction as light is penetrating through. Let's say you got water, for example. So you have the sun, right? You underwater, you look up and you see the sun and rays of light coming through the water. That's refraction. And then when you see light shining off the top of the water, that's reflection. And then you have color loss too as well underwater, which is due to diffusion because the light beam scatters. So as the longer the wave or the deeper down you go, the less concentration of light is. Anyways, so with builder's levels, theodolites, all that, it works the same thing, except they're not reflective, because reflective is for astronomical telescopes and stuff, but they're refractive telescopes. So it's just basically a series of lenses that get smaller and smaller and smaller, and it brings in the light and gradually focuses and magnifies the light. And then, you get the focal point that you always hear about. And then it comes out on the other side. And so you're manipulating light and concentrating light to be able to see further than you would see with your human eye. And so these surveyors, back in the day, and they've been surveying for a long time, right? 1800s. That was kind of the first, use of telescopes outside of astronomy, right? And to this day, we still use builder's levels and transits and theodolites. We'll take pictures outside, but when you go inside, you can't.
Yeah.
They got a big sign saying no.
So you just leave them in your car?
Yeah, just leave them in the car, I would assume. Everybody's doing the same thing, pal, so it's not like... And it's the government, because this is like an official... This is like NASA. We're basically going to NASA, but...
Yeah, we're going to a government facility.
Our version of it.
Yeah. Look how pretty it is. It reminds me of the Yukon a bit.
It does kind of. I was thinking about that too, actually.
It's got the brush look.
It's that arity, sagebrush, all the sagebrush. Oh, turn off all the devices. Yeah, see? Where is it? Well, there's a salt lake.
I'll get it.
Yeah, there's a salt lake there, everybody. That's cool. You don't usually see those.
Yeah.
Pretty self-explanatory, but it's a lake with salt in it. Or high salinity, I guess. The proper terminology.
I lost my phone.
Oh, there it is. Okay, yeah, there it is. Okay, so those half pipes there, what looks like, skateboard half pipes, that's CHIME. So that's the Canadian hydrogen intensity mapping experiment, and that's studying the redshift of the universe, right? The redshift of the cosmos. That's the synthesis telescope. You see those seven. It's 7 total telescopes. They do something called aperture synthesis with it. So to see really far into space, you need a massive telescope, right? Because you got to pick up waves. Like the further away something is in space, the longer the waves are and the harder they are to detect. Because the bigger they are, the less intensity they have, the less amplitude. So when you have aperture synthesis, or what they're doing there, a synthesis telescope as they call it, which is 7 telescopes along a certain area. Each one of those telescopes is its own telescope, and they have this thing called interferometric data, which is basically they just take interference measurements. So each one of those telescopes has a measurement, and it gets fed into this computer, and it all gets cross-referenced, and then so those little telescopes become one big telescope. And they actually do that around the world. The other telescope we're going to view was one of the first telescopes used in very long baseline infometry, which is basically like a telescope in Hawaii, a telescope here. telescope in the it was about 8 telescopes, and they basically they triangulate them, and then all the readings and stuff are put into a computer, and they basically, it's called aperture synthesis. So you're synthesizing an artificial image through interference measurements. We're gonna take a look now and see if the gate's available. Oh, the government, or National Research Council of Canada. This is one of the facilities. That's Chime there. John A. Galt, he was the founder of this facility in 1960. He was the one that actually kind of helped pioneer that very long baseline infometry stuff that I was talking about. That was him. We're going to go see the telescope that's named after him. He helped install it. He was instrumental in all of this. University of Toronto guy. And University of Toronto, McGill, and University of British Columbia all work together at this facility. They all share the data. So this is the synthesis telescope I was talking about, right? This is Chime. They have a solar flux monitor, 10.7 centimeter wavelengths. And then the John A. Galt telescope, right, with the visitor center. So, but this is the aperture synthesis that I was talking about. And then they're developing technology over there, obviously, research and development, engineering. Canadian observatories as well. These are all the observatories. So we finished the Dominion Radio Astrophysical Observatory, or DRAO, as it's the acronym known. Absolutely incredible. There's like kind of a trend appearing, this astronomy thing. It's quite hard to put all this stuff into words, and I'm not talking about the science aspect of it. You know, like that can be difficult at times, but just the scale and like how relative everything is in the universe. It really gives you an idea of, like, not to sound cliche or anything, but we really are small and tiny, and we're part of something so much bigger that we really have so little understanding. Like, you're talking to astrophysicists that studied at some of the best universities in the world, and they're like, we just don't know. They're like, we do not know why it does this. It doesn't necessarily make sense according to what we understand, but then they're like, there's probably things we're missing, right? So this facility it's the only facility in the world that has the chimes, that half pipe that studies hydrogen and redshift. It's the only facility in the entire world that has that. They took us through the facility. We got to go to the one of the main telescopes control rooms, and go see tons of old analog equipment, kind of see like the true past of, like, you know, what astronomy was before we had technology. And it's kind of ironic. They were kind of making a joke about it with them there. It was places like this, you got all this crazy technology and crazy science happening, but you can't use your phone. You can't use computers. Like, when the people that stay there, the staff housing, they can't use their computers or phones outside of specialized isolation rooms, because our phones and all of our stuff causes interference, and it makes it really hard for them to study. There's just certain wavelengths they can't study, either because of the legislation, the way it works for, certain bandwidths and frequencies are bought, like for radios and all that kind of stuff, right? Like my VHF and stuff. They can't study them for that, or just literally, like, some frequency spectrums are so blocked out, there is no way to study it, because it's just white noise all the time, basically. So it's a pretty incredible experience. They're open from April till October, 10 to 4. You got to walk in. You just walk down the thing. There's no electronic devices at all, and please, as a courtesy to the people, try and turn off, like, obviously your car and stuff, you can't turn it fully off, but make sure you turn off all your electronic devices, because it really, like, they were showing us interference pictures of, like, the interference they pick up from just a car driving by the facility, and it really hinders their ability to observe. So yeah, there's two types of astronomical telescopes. You got alt-azimuth or altitude-azimuth telescopes. So all that means is basically you've got the vertical axis, the altitude, and the azimuth, which would be the horizontal, right? And they're kind of limiting because as the Earth rotates, so let's say you want to see an object in the sky, if you fix that alt-az telescope on it, and you're observing for, let's say, a couple hours, or you're doing like astrophotography, as the Earth rotates, the image that you're trying to observe is going to be obscured, and it's actually going to move out of the telescope's line of sight, because the Earth is rotating and you're not, that telescope isn't, right? So you're just gradually going to just lose what you're seeing. So they have ways to, like, you know, you have to manually adjust it. There's equatorial mounted telescopes. The Earth has a polar axis, right? North-south. So it's on an angle of 15 degrees. So what you do with a equatorially mounted telescope is you position it on 15 degrees facing in line with the pole. So you literally want the telescope on the same angle and tilt as the Earth. And then it has, like I was talking about, the graduated circles. So in a graduated circle, you have these degree, minute, hours, basically, which it's very complicated, but it's basically a way that angles track over a certain amount of time. And so these telescope mounts, they have these graduated scales, and sometimes it can be manually adjusted, or it can be adjusted with an electric motor, and it rotates in an opposite rotation to the Earth. And basically, as you're like looking at the object, the telescope will adjust to keep the object you're observing in the picture. The one thing we should also be made clear that one of the guys was saying, he's like, if you take nothing else away from this observatory experience, understand that radio waves are not sound waves, it's light, right? Anything on the electromagnetic spectrum, whether it be ionizing, or which be like, you know, heavy radiation, UV, gamma, like, you know, suns and all that kind of crazy stuff, or non-ionizing microwaves, it's all light. For sound to exist, you need air, right? Sound waves move air, like a speaker. What all speakers do is take an electric signal and use that electric signal to move air at a certain rate, and that's what actually causes the sound to be produced, right? So same concept in space, right? There is no sound in space. Space is a vacuum. Space does not have sound, which is also kind of like, you know, just think about it. You have massive supernovas coming out everywhere, and there doesn't sound like anything. You have bodies the size of our galaxy colliding together, and they don't make noise. And also, there is no explosions in space. Like, it's all just ejections of light traveling over long distances. Like, the universe is 13.5 billion years old as we observe it from here, right, with the light, but it actually isn't. It's actually 26 billion years if you take in the redshift calculations and cosmological math and all that other stuff that you PhD guys are doing. It actually ends up being 26 billion years old. And it's getting bigger, and it keeps expanding, and we don't know why. So it's like, and I asked them, I was like, so if something was to happen now, a couple billion light years away, we'll never see it. And they were like, yes, that's correct. So it's the only time you're ever seeing stuff when you look into the sky is you can only ever see the past. The amount of things that are happening in the universe that we still don't understand is amazing. But the one thing I thought is really important to mention is it's a government-funded research facility, and the biggest part of that is it's not because they're hiding anything or it's secrets and all that, right? You know, everybody knows the government does that, but it's because radio astronomy is not a lucrative business, right? You can't really make money off studying radio waves in space, right? It's not a business. So it's basically charity, right? So the government takes over, and they'll use taxpayer money to fund that facility, and the equipment that they're building there is incredibly sophisticated and not cheap. And they're really big on getting civilian people in there to look at the facility and understand what's going on, because it's important. It's how we understand where we are in the universe and like how we relate to it. And ultimately, if you want to time travel or do any of this other stuff that you see in Star Trek and all these cool little realities that we fabricated, this is the step forward to do that, right? In a real down to earth, practical 3D way.
Now I need somebody to volunteer to stand behind the telescope and look at both sides of the opening and make sure I'm in the middle. I have to run back and forth. Maybe somebody can do that.
Whoever wants to.
I think we're pretty much there.
Yeah, feels like it.
I'm just going to put some red light on and kill them.
Okay, so it's quite late at night here, so we just left the Newton Observatory, and I can't really put it into words if I'm honest. I highly recommend it. We got to look through a state-of-the-art electromagnetic controlled telescope, a $300,000 telescope. We saw the moon, we saw Vega, we saw Polaris, we saw M97, we saw a whole bunch of galaxies. That's it for tonight.